Hello, so now that we've talked about the hazard function and its connection with the failure rate, we're ready to talk about Weibull distribution. So let me just introduce you. Here's the PDF of this distribution. It looks a little bit complicated. Easier to see what's going on is the CDF down here. And that's got the variable x, and then there are two parameters. There's the shape parameter k, you find that one here up in the exponent, and there's a scaling parameter lambda. Think of the scaling parameter just as something where we can stretch and compress the distribution. So not much to be said about that. It's just for matching it to whatever data you've got or what you want to model. The more interesting one is the k. So for k equals 1, Weibull is identical to exponential distribution. For k equals 2, we've got a Rayleigh distribution. And yeah, let's first of all, we don't know these two, but you can look them up if you're interested. Let's first of all get just a bit of a feel for this whole thing. So shape parameter 0.5 gives us quite a steep PDF. PDF goes down really quickly, monotonically falling. K equals 1. So here it kind of comes from infinity. Yeah, comes down. K equals 1. We seem to start here at a fixed point. I think it's 0.5. So already quite a change. Then k equals 2. Very different shape. Now the probability kind of density rises. Little bump here, and then it goes down. That's the Rayleigh. And I've put a few more. K equals 4, so very pronounced peak here. Almost looks a bit Gaussian. And last one, k equals 8, and that's quite a distinct peak here. Alright, so we know what it looks like. So what's interesting about this Weibull distribution? What does the shape parameter really do? And we want to look at the hazard function for this. So here again, hazard function. We have the PDF. Yeah, that's like our absolute failure rate. And we divide that. That tells us how many, if you have like 1,000 parts, how many in absolute numbers are failing. But we normalize that with the survival function. That tells us how many parts are still working. So that gives us a failure rate per item, or like a hazard. Yeah, how dangerous is it for an individual item that breaks at a certain time t? And if we look at k equals 0.5, like the first one that came steep down from infinity, we can see that the hazard is going down as well. So that means in our system an individual part is very likely to break early on, and then it's less and less likely. So not only the PDF is going down, also the hazard. K equals 1 was also monotonically decreasing PDF, but the hazard is constant. This is basically the continuous version of what we saw with the dice, with the binomial distribution earlier. PDF going down, but like hazard constant, or with the coin flip it was, sorry. And for k equals 2, we get an increasing hazard, and that's interesting, like linearly increasing hazard, because what we saw for k equals 2 was the PDF, I mean, it goes up in the beginning, but then it has like a distinct decrease in the second part. Yeah, that's because there's not many parts left. So that all matches up, and yeah, we can basically use the shape parameter to model different scenarios and model like different things, or we can like fit it to data we have and find out how our parts are doing over time. So let's look at an example. Let's think of radioactivity, and let's assume we have a lump of uranium and we want to, uranium spontaneously decays. The big uranium atom like falls apart into two other smaller parts. And how would you describe it? What shape parameter do you think we should use for something like that? Obviously it's an example a bit out of physics, which is my background, so I find that quite exciting. If you haven't ever heard much about radioactivity, don't worry if you didn't really guess the right answer. So k equals 1, basically these decays, they're completely independent of each other. Like each atom kind of just spontaneously decays, they don't influence each other. So it's a memoryless process, we say. So it doesn't matter what happened before, what other atoms are doing, like only the moment counts. And k equals 1 is the shape parameter that describes something like that. Let's go to something more maybe intuitive. So New Year's Eve, lots of people buying fireworks. You light one of your big fireworks and then you wait for the big bang. What shape parameter do you think would describe the time, until the thing explodes? I'm fully aware that the different interpretations can be counted. My argument would be k smaller than 1, because I think the hazard is in the beginning the highest. You light it, and okay, maybe not for the first split second, because it can't go off the instant you light it, but there's a really high, if you think of here's time and here's the hazard, then I think after you light it, the hazard is really high that it goes off. But after your bomb has been sitting there for a good 10 minutes and nothing has happened, I think we're good to say it doesn't work, or the fire has gone out or something, and then the chances that it still detonates are just really small. So I would see like a decreasing hazard in this. Maybe Weibull is a bit too simplistic. Obviously, maybe would like also have like an increasing bit at the beginning, but we can't model that with Weibull. Just the last example, just to get the feel, and Andreas in his lectures on quality management is gonna take you through a lot more things with Weibull. There's just a taster here. So light bulb breaking after a certain time. So what shape parameter would we use? Have you guessed? Yes, k bigger than 1. If you buy it, then you would assume, and here's the hazard, when you buy it you would assume the hazard is fairly small, the new light bulb breaks. But if you have a light bulb that's already 10 years old, I guess the hazard would increase. At some point the thing is just worn out and it's getting more and more likely that it's at the end of its life. So yeah, different scenarios, and they all can be kind of in a simple approach be modeled by Weibull distribution. So that's why it's quite useful. You can use it on MATLAB, WBL PDF and WBL CDF, and obviously in Excel it exists as well in the Weibull.dist. Okay, excellent. Thanks very much for your attention, and I'll see and hear you next week. Bye bye.